Today we'll be talking about vectors, which you guys read about. And we already mentioned that a vector is different than a scalar in that it has an extra piece to it. So instead of just having magnitude, you have magnitude and direction. And so vectors you could use to describe the flow of water. So here is a vector field. All these tiny little arrows are representing how the water is flowing. So the length of the arrow talks about how fast it's going there, and then the direction of the arrow talks about which way it's going, right? So in a current, you could have it, kind of moving around different, rocks in, the bed of something, right? So it doesn't necessarily all just flow one-dimensionally down something. And so vectors are useful when you start to think about things in 3 dimensions, because direction is important. And there's a couple of simple examples that you could think about of where a vector is way more important than a scalar. Well, I guess it's incomplete to just give the scalar amount. So let's say that you lived in a small town where there's just one road that goes through the whole town. And you're standing on the side of the road and a car approaches you from down the road, and they ask you where the library is, and you say it's a half a mile, right? So they're on one road and they just have to go, 1/2 a mile and they'll find the library. So it's pretty straightforward that that direction makes sense, right? So that's enough information for them. But what if instead you had a little bit bigger town, and this town had multiple streets, and so you're sitting here in an intersection, and a car approaches you here, and they ask, where's the library? And you're like, it's a half a mile. And they're like, okay, but where? Because it could be, any of the points along the circumference of this circle is a half a mile from you, right? And so theoretically, the library could be at any one of those spots. So you haven't really given them enough information to figure out where the library is. You also need to give them a direction. So if you said something like, it's south, right? Then you have specified a location. Or if it is northwest, then you have specified a location. So in some cases, a scalar is okay, like how many apples did you have for lunch today? 32, right? That's enough. But if you're asking something like, how do I get to, the nursing building? A number, just a number is not going to be enough. You're going to confuse some poor touring family. So this again just kind of points out a scalar. It can be positive, negative, or 0, and things that are scalars include time, distance, speed. Vectors have both magnitude and direction. So the magnitude is a positive number, and then the negative corresponds to the direction. So you can imagine on a Cartesian coordinate system, positive and negative in the y direction means different things, right? So positive y, negative y. So then that negative and the positive is associated with the direction when you're thinking in Cartesian coordinates, right? So really a magnitude is just, how much. And vector quantities, you will often see them typed as bold-faced, but when you're writing it, it's hard to write bold-faced, so we put a little arrow on it. It's very cute. Well, you'll see. I'll write them a bunch. But just a tiny little arrow over the top to indicate that this quantity is a vector. So a vector that you are going to be seeing a lot of and learn to love is the position vector. So the position vector is represented by usually R. And here you'll notice that it's bold. Again, when you're writing it, I would write it something like this. And I have a very stylized arrow because I write these a lot. So instead of having to pick my pencil up and go like this, I just write it like this. Saves you that split second that could be the difference between passing and failing, right? Because that's how closely I time my tests. I'm just kidding. But so if you can do this if you want, or you can make it a very pretty little arrow or whatever your heart desires. But just sharing how I do it. And then the magnitude is written as just a regular letter because the magnitude is a scalar. It's just the amount. It doesn't. So that's we've stripped off the direction information. The magnitude is just the size of the vector. It doesn't have to do with the direction. And so we just write it as a normal or italic sometimes if it's in a presentation. It's also hard to do italic when you're writing. But so just a regular character would represent the magnitude, which is the scalar part of the vector. Sometimes I'll also, if I really want to be explicit that I'm talking about magnitude, I'll write something like this. So I'll take my R and I'll go like this. So it's this absolute value sign is something if I like really want to emphasize, and it's not like I can't do italics. So I'll sometimes write this. It means the same thing. It's the magnitude. Or if I just write this and I forget the vector sign, then I am literally meaning it's a scalar. But sometimes I forget. So catch me if I am talking like, oh, here's the vector, and I don't write the little arrow. And then the position vector has a magnitude of distance, and so the units that are associated with it are units of length, so things like meters, feet, inches. And when you're drawing vectors, so I mentioned, so for a Cartesian coordinate system, you would represent a vector as an arrow. And the length of the vector is the magnitude, and then which direction it is the direction of the vector. So it's a nice, neat way to represent these kind of on your paper. And for a lot of this class, we'll be interested in components of a vector. And so what these are, in order to specify the direction, first we have to have a coordinate system. Oftentimes it's your standard x and y. It could really be anything, but I would say 99% of the time we'll be using x and y coordinate system. And I'm most familiar with writing it this way, right? So I draw it like this. You could, in theory, kind of move it around however you want, but it's easiest, I think, for everyone to keep it like this. And so when you're drawing your vector, since the length corresponds to the magnitude, right? So if we're thinking in distance, position vectors in distance, the size of it, this length is going to be the distance. So you could plot a point at the, so if I give you a vector, let's say, I'm going to walk, half a meter this way and then a meter up. Those aren't the right components, but so then that would give you like a point to draw, and then your vector would be just the distance that you've traveled totally, right? So you could plot your little point as like your end point. So this is like start, finish, and you're going that way. So your position has changed from, the origin to that little point up there, and you are moving in that way. So that's why we drew the arrow that way. So its final is at the tip of the arrow. And so, in order for this thing to be a vector, it has to have a direction and a magnitude. So you have the magnitude written here, and you'll notice it doesn't have a little arrow on it. And so it's 1.5 meters is the distance, the magnitude of this vector. And then the direction, we need to specify the angle in order to look at things like components. So you need to know exactly which direction it's going in. So it's 25 degrees counterclockwise from the positive x-axis. Is how I would describe this vector. Now, when you're thinking about components, these are, I think your book refers to them as rectangular components. You could think of them as projections if you're really into math. You could almost think of it, and like the word projection kind of hints at this too, you could think of it as like the shadow, right? So you have this R vector, and you can imagine like, here's my x-axis going this way, and then y-axis is coming out to the ceiling. And so my vector looks something like this, right? It's at some angle, 25 degrees, counterclockwise from the positive x-axis. And so what these components are, the x component is if I took a lamp up here and I shined it, perpendicular to the x-axis so that it lays a shadow on the x-axis, that's my x component. Right, so you see, this would be like the shadow that it would make if the sun was just raining down on it from perpendicular to the x-axis. And then you can also think about the y component being a projection or a shadow onto the y-axis. And you'll notice that whether I shine the light this way or this way, the size of that is going to be the same, right? So the size of the shadow if I'm going this way is going to be the same as if I shined it this way, as long as I'm perpendicular to that y-axis. So it's kind of like a shadow. It's these components. And so what these components sort of do is, you can kind of see here, because it's kind of lined up, is that it'll make a nice little right triangle, right? And so those are useful for trig things, right? So if you're thinking about angles and stuff like that, you can see a nice relationship between these components and the angles that maybe your vector is making with different axes. And so here is, a very explicit picture of it's a right triangle. Right? Because your x component is always going to be perpendicular to your y component. because your x-axis is always perpendicular to your y-axis. So any shadow that is on the y-axis is going to be perpendicular to a shadow on the x-axis, which makes a nice little right triangle, which is very nice and useful. So to figure out what these components actually are, you use a little bit of trig. And this is a little bit quick and dirty. Like we did this more explicitly when we were talking about the quiz. But you can break it down. You can take it a step back and see how these relate to your trig function. So we were using cosine in the quiz, right? And we know that cosine is the adjacent of the angle over the hypotenuse, right? So cosine of theta, and so theta is in that corner on the lower left. Cosine of theta is equal to the adjacent to it, so that's a sub x, right, the x component, over the hypotenuse, which it's a vector, but the length of it, right, when you're working with trig, you're using just kind of the length of that, the magnitude of that vector. So the magnitude of a vector is a, right, or I could do the little vector with little absolute values if you want. So this you could solve for if you know theta and you know what a is. You could figure out what ax is. You just multiply by a on both sides. And so then you get this expression there. So you get ax is equal to a times cosine of theta. You can do a similar little exercise on your own to convince yourself that the y component looks like this. Okay, so that's how you figure out how big is that shadow. And this little equation is how you figure out how big is the shadow. And then you also know other things about right triangles too, right? Like what is this thing right here? What theorem is this? Pythagorean theorem, right? So this is a squared equals this side squared plus that side squared, right? So you can solve for all different sides of this. If you have the components, you could get the hypotenuse, right? If you know, so you can solve for angles, stuff like that.
What's the bottom right one?
So if you were thinking about, so let's say that you had the x and y component and you wanted to find the angle. How would you go about doing that? So this is kind of the abbreviated solution. But so if I gave you, instead on your quiz, if I gave you a triangle, I said this side is A and this side is B and here's theta, and you know what this is and you know what this is, how would you solve for theta? It's a trig function. There's a strong hint on the slide. Tangent. So TOA, right? We have adjacent and opposite, right? So you can use tangent of theta is equal to the adjacent. Wait. The opposite over the adjacent. Yeah. I'm telling you, when you're in front of people, IQ drops by 50 points. But all right, so opposite over adjacent. And then we can do a little bit of solution, right, to find theta. So how do you find theta in this?
You have to do the inverse tangent.
Inverse tangent, arc tangent, whatever you like to call it, is what you have to do. Your computer calculator does it. So theta is equal to the inverse tangent of, in this case, a over b. In that picture, it's the inverse tangent of a sub y over a sub x. So it's really just trig because we've turned our vector into a nice little right triangle. So all cosine, sine, tangent work, Pythagorean theorem works. So that makes it really useful because these are things that you have seen. And so, maybe you've forgotten about it and it's like a little rusty, but it will come back very quickly. Okay, so I said that the magnitude of the vector has to be positive, but components can be negative. And we'll talk a little bit more about this for we'll talk about unit vectors and what those are, and it has to kind of do with that. So your components can be negative. So depending on which quadrant you're in, it sets what's going to be positive or negative. So if you are in the first quadrant, so I believe it goes 1, 2, 3, 4, makes a little C for Cartesian, right? So if you're in the first quadrant, then you have a positive x component, positive y component. If you're in the second one, you'll have a negative x, right, because you've moved past that y-axis into the negative x's. And and a positive y, because you're still above the x-axis. And then it kind of makes sense as you go around. And this is that warning that I gave before about calculators. So double check that they make sense. Like draw a little picture of like what your vector is if you're solving for an angle, because it might give you an angle in the wrong quadrant. So like relative to an axis, it might be the correct angle, but it's like in the wrong quadrant, so you might have to add 90 degrees or something like that. So just be careful if you're using your calculator on things, that it's an angle that makes sense. And you can also sometimes give angles with respect to the y-axis. So this, on your unit circle, pi over 3 would be like here, pi over 4, pi over 6, pi over 2, that sort of thing. But you could also, so that is relative to the positive x-axis. That's kind of your standard way of defining angles. But you could explicitly say, I want a vector that is pi over 3 counterclockwise from the y-axis. So it'll look like this, right? But that would really be, if you're going from the positive x-axis, that would be what, 4 pi over 3? No, this would be pi over 2 plus pi over 3, whatever that is. So just be careful where you're defining it from, what direction you're going in, because you could also say, oh, I want to go clockwise. So positive angles are going to go counterclockwise. Negative angles go clockwise. So just be aware of which way you're going, where you're starting from, because all of those things could change your answer. Just like in the situation where you're describing how to get to somewhere. It depends where you're starting and what direction you tell them to go from there. All right, so this brings us to our first example. And you get to play along. So good. And these, I like to do these a lot because there's some topics where you just follow along and you're like, yeah, okay, makes sense. And it's like, okay, like now do it. And you're like, wait, what? And it happens to me too, where like the person's so convincing when they say it, but then when you actually have to do it, it's like, oh, So that's why I like to include these in it. So I try to get them in every single lecture. So the first example that we have is we have a hiker that begins a trip by walking 25 kilometers, 45 degrees south of east from her base camp. On the second day, she walks 40 kilometers in a direction 60 degrees north of east, at which point she discovers a ranger's tower. Determine the components of the vectors representing the hiker's movement. So her first movement is labeled as A. Her second one is labeled as the vector B. So she walks, oh, and it's cut off there, which is very disappointing. I will write it out, what the numbers are. I'll draw the picture with things. Okay, so we have a hiker, and she is going to go A, which is equal to, A is 25 kilometers. We'll just say magnitude of A, 25 km. And then she's going to go this way, which is B, and the magnitude of B is 40 kilometers. So she gets much more in on the second day. Just invigorated by nature, I suppose. And so my question is, what are the components of these two vectors? So these are the magnitudes and then the directions. This is